So I'll be talking about volatility and arbitrage. And the idea is that in an equity market, if there is adequate volatility, then there's relative arbitrage. And we'll investigate what that might mean when there's long-term arbitrage and when there's arbitrage over a short period of time. Now, I'm dealing with equity markets, and so essentially there's no cash numeraire. I've eliminated the cash numeraire. We use the market itself as a numeraire, and so we'll talk about relative arbitrage rather than classical arbitrage. However, they both seem to be very similar. In fact, sometimes they'll overlap. The market that we're going to have, we use the logarithmic representation here. Can you see that pointer? Yes, okay. Can you see the pointer? Yeah, okay. Yeah, we use a logarithmic representation, okay? We have these stocks, n of them represented by positive continuous semi-martingales. And this is the standard representation. You have at least as many Brownian motions driving this thing. The processes, the gamma process and the Xi processes are measurable, adapted to the Brownian filtration, locally integral or square integral is whatever they have to be. Okay, now this is equivalent to the standard representation because we could have log of x of xit over xit, just there's going to be an Ito correction term in there, and then this goes just back to the standard situation, so there's nothing special about it. However, looking at it logarithmically turns out to be quite convenient from our point of view. We have the market weights. Oops, I'm hitting the wrong button. Okay, I'll get this better. The mu i's, they're the market weights, they're the value. These things actually represent, the xi's represent the total capitalization of a stock, okay? So the whole market is the sum of these, and the market weight would be the value of one over the value of all of them. The market weights play an important role here. We have a covariance process, sigma ij, okay, it's the covariance, it's actually the rate of quadratic variation of the log xi and log xj, and you can see it be the product of these, the dot product essentially of the x's. If the eigenvalues of the covariance matrix sigma, made up of the sigma ij's, are uniformly bounded away from 0 in the interval 0t, then we say that the market is strongly non-degenerate over that interval. Now, this type of condition is used from time to time. It's a very strong condition, really. Because what we're talking about is we have this say 5,000 stocks, and so we're looking at the smallest eigenvalue of 5,000 by 5,000 random matrix, and it's pretty courageous to assume that that's going to be bounded away from 0. What is the bound? So we're trying to get rid of this whenever we can do it. But I'll state it because it comes into play, and then we try to take it out of play later on. Portfolio is defined by its weight processes. They have to be bounded, measurable, adapted, and so forth. And the boundedness is important here to make sure the portfolios actually exist. The portfolio value process, we define these things by the weights rather than going and defining the value directly. We get this equation, which is really sort of like Harry Markowitz's equation. If we had a d log dz pi over z pi, and there's dxi over xi there, that would just go back to the standard representation with the weights and so forth. So what will happen is we're going to get an extra term here, which is called the excess growth rate process. And that incorporates all of the Ito correction terms. So it's pretty clear what it's going to do. It's going to have a lot of variances and covariances showing up. And it turns out to be, this is what it's written as pi I, sigma I, and so forth. This turns out to be a very important function in what we do. And it's straightforward to derive it. You just put in all the correction terms from the old Harry Markowitz formula. The market portfolio, which is important, after all, we're going to use this as our numeraire. It's defined by the market weights, which add up to 1. Okay, by the way, I forgot it was written there, but I didn't state it. The portfolio weights have to add up to 1. They don't all have to be positive. You can go long and short things if you want. But we're adding them up to 1 so that the value process makes sense. You can also go further than this if you feel like and have investment strategies where perhaps the weights would add up to 0. You'd have a long strategy minus a short one. Well, we're not going to bother with that. We're just going to talk about portfolios. They always have a positive value. The weights have to add up to 1, but they don't have to be positive weights because you can be short in some of the positions if you'd like. Okay. Now, we know that the mu i's add up to 1 by the way that we wrote them. Okay. And so you get a market portfolio. And if you started out at the beginning value of the market, then it adds up to what the market value is. If it didn't, that would be a problem, obviously. Okay, IJ, relative covariance process, tau IJ, it's defined for IJ. Okay, it's now actually, if you just look at the cross variation between log mu I and mu j, which is written like this, it gives you this relative covariance process, and you can write it out if you wish in terms of the sigmas, which we'll look at again in a minute or two. This is just basic boilerplate stuff that we have to go through. A market is diverse over the interval 0t if there exists a delta such that all of the mu i's are bounded away from 1 by delta. This is a weak antitrust property. This is not a very strong condition. Any half-decent market is going to have this. Even if you go to Finland in the heyday of Nokia, I think it never got over like 70% of the or so of the market. So if you had a delta equal to 0.25, it would have worked. But you can think of delta 0.01 or something like that if you wish. But whatever. Now we actually have a lemma. We can already prove something, amazing as it may seem. If the market is strongly non-degenerate, here's a strong assumption that we want to get rid of. And diverse, here's a weak assumption that we're willing to deal with. However, we don't like diverse either, particularly. We have using conditions that we're not terribly happy with because diversity has nothing to do with volatility. Remember, I was advertising volatility at the beginning of the talk. So we have one overly strong condition and one condition on the structure of the market, but we get a lemma out of it, and it's worth looking at it. Okay, suppose there exists, okay, if that's true, then there exists some epsilon bigger than 0, and all of these taus are bounded away from 0 by this epsilon. They're all bigger than epsilon. Proof is easy, which is good. Okay, you write this vector x of t, which is essentially mu minus 1. You put a minus 1 in the ith position, all right? And you can see tau ii is just going to be x times sigma. This is matrix multiplication times the transpose, all right? Now, the strong non-degeneracy, you can cite that, and you have to have a positive constant, so that's bigger than or equal to this, okay? That's the smallest eigenvalue, okay? And then you see that this value has to be bigger than the value of just one of the things squared, so it's bigger than that. And because of the diversity, you get this thing bounded away. So under those particular circumstances, we can bound the tau i's away from 0. This is going to be valuable to us in the future. Relative arbitrage. Okay, for a t bigger than 0, you have relative arbitrage exists versus the market on 0t if first, by the end of this thing, for this portfolio, by the end of the period, you are never going to be behind the market, and you might be ahead of it with positive probability. It's strong relative arbitrage if you're sure to be ahead of it at the end of the period. Now, you need a few extra conditions that I'm not bothering with here. You have to have because you want to disallow doubling strategies. So essentially, you're going to have to say that this ratio is going to be bounded from below and things like that. I'm not going to dwell on that, but you'll see that in the things that we structure, they're structured in such a way that that's sort of automatic. Okay, we're interested in conditions under which volatility, whatever that means, produces relative arbitrage, and we'll try to make all of this stuff precise. But we're looking at relative arbitrage versus the market. We'd like to be able to beat the market. That's what equity managers are supposed to do, okay? So, suppose S is a positive C2, twice continuously differentiable function defined on a neighborhood of the open simplex in Rn. Okay, the simplex is the set of points where the coordinates add up to 1 and they're all positive, okay? S generates a portfolio pi, then S will generate a portfolio pi such that pi follows the value process of pi will follow this plus a function, a drift process that has bounded variation. In other words, there are no extra stochastic terms here. We don't have any extra stochastic integrals. Now see, this is very useful for proving arbitrage, because if you have a decent function S, you can control the size of this, right? And then if you can figure this thing out, you'll be able to tell what happens to the portfolio with probability 1. That's very convenient. Okay, now let's see what the rest of this says. That's a bounded variation, which is good. Okay, the weights and drift processes are determined by the partial derivatives S. All right, now it turns out this is pretty easy to prove once you know what you're trying to prove. Okay, you'd use Ito's lemma a bunch of times and so on and so forth, and you can get this done. And this is fairly powerful, although it's very easy to really establish. Turns out that the pi's here are determined by the essentially the gradient of the of log of S, and the theta here is determined by the Hessian. And so you can get other propositions and theorems and so forth about this if you wish. Like if S is not only C2, but it's also, say, concave, in other words, the maximum is in the middle, then you can show that that theta actually is going to be positive and possibly bounded away from 0. That is, the derivative of it is. And if it's convex, which is a bowl-shaped thing, then it would be negative. So this is a useful piece of machinery to prove arbitrage. Okay, proposition 1. So we already have a proposition now. If there exists an epsilon bigger than 0 and just one of the k's in the set here, where tau kk is bigger than epsilon for all t, then there exists strong relative arbitrage versus the market over 0t. This was proved, a version of this was proved in a paper that I wrote with Yannis Karatzis and Kostas Karderas, who may not have left yet. I'm not sure. In 2005, okay? Okay, so what you do is you take a p that's bigger than 1 and you consider a function s which is equal to x sub k, it's the same k as we have up here, to the pth power, okay? So it's a higher than 1 power of p. It's defined on the simplex, okay? So it's a function. It's going to generate a portfolio. And it turns out these are the weights for the portfolio. And this is the equation for the performance of the portfolio that comes from this. Now, what does this portfolio look like? Okay, this is in the kth position. You're going to have p units of this kth stock. And you're going to have essentially minus p minus 1 units of the market in this portfolio. And it will follow exactly this equation down below. So let's look at what we have here. Essentially, okay, it says you have p dollars of xk and minus p minus $1 of the market portfolio. That adds up to 1, of course, if you did it. Is that correct? Yeah, it does. Okay. And then this is the integral of what we saw below. All right, now how bad can this get? It turns out here actually we're trying to do worse than the market portfolio now. In a moment, I'll tell you how we get out of this situation. This can only be as big as 1. It can't be any bigger than 1. So that goes away. And so this will drop down to a less than or equal to here. We know that this is bounded away, is bigger than epsilon. And so you get this integral and you get the p minus 1. So now if you look at these, the p terms, if you make p big enough, this is going to be, that's negative. So this is actually a positive number. But if you make p very large, you can force this thing to become negative. So for p large enough, then z sub pi is going to underperform the market. But as Donald Trump would say, we don't like losers. So what we really want to do here is, what we do is we short a little bit of this portfolio and we immerse it in a vast sea of the market portfolio. And this is going to be an all long portfolio that comes out that will outperform the market. So we actually have now a situation where you have relative arbitrage. Let's go back and see what this situation was first, okay? Sorry. We're looking at this thing bounded away from 0. Remember, all of these will be bounded away from 0 if we have diversity and strong non-degeneracy. So we're seeing a number of things here now that will start to give us arbitrage. The problem with this is only, we still have to invoke this strong non-degeneracy in order to get this to work, and we'd like to get away from that. Okay, so that's finished. That one now is done, okay? We want to look at the market excess growth rate. Okay, so we have a definition of the excess growth rate, and we consider it for the market. Okay, so we're going to get these weights here, and it turns out that we can write, it turns out that if you sum mu I times sigma I mu, so summed over C, that just gives you mu, sigma mu mu. So it turns out that this pair of terms is equal to that term. And this, as we recognize, is just the tau I term again. So it turns out that gamma star mu, the excess growth rate of the market, is a weighted average of the relative volatilities. And this is what we would like to use to measure sufficient volatility in the market, adequate volatility. And it's almost good enough, as we'll see later on. Okay, we have a lemma here that says, it's an awfully easy lemma, it's embarrassing. We have tau I bigger than epsilon for all I, then gamma mu is going to be bigger than epsilon. Yeah, that's pretty easy. You don't even need a proof for that one. Okay, the next one is we look at what gamma mu star actually looks like, okay? We want to be able to bound this away from 0. We'd like to use this thing bounded away from 0 as our adequate volatility. This is the integral of it. Okay, so this is the integral of gamma mu for the US market, which has thousands of stocks in it, from the CRISP data starting in 1927 and going up to a few years. It's probably, I don't know when this thing stops, but it was probably 10 years ago. I don't have a newer one. But in any case, the slope of this is what we're looking at. Do we think we can bound that slope away from 0? Essentially, for the slope to hit 0, all the tau i's are going to have to go to 0. So it doesn't look like it's something that's very likely to happen. It seems like a fairly weak condition. And historically speaking, over the last 80 or whatever number of years, we've certainly been in a situation of that nature. So gamma mu star bounded away from 0 is the condition we're going to be looking at. All right, now what can we do with this gamma mu star? That's what we're going to try to see now. The entropy function S, this is, I'm not sure if this is the Gibbs entropy or the Shannon entropy. It sort of depends where you're speaking. If you're speaking at Yale, it's Gibbs. I'm not sure where else it might be. But in any case, it's a standard function. People are familiar with it. And this can be applied to the weights. So this turns out that it's going to be a generating function. At status, it's positive and it's less than log n. Value 0 is attained only on the vertices of the simplex, which are outside the open simplex, by the way. And log n is attained only when all the x's are equal to 1 over n. That's pretty simple to see that. Because of the fact that it can be equal to 0, which is inconvenient for us, what we're going to do is going to add a constant, non-negative in general, but positive constant, and have a generalized entropy function. Now, what's interesting about this is, as a generating function, you see this will, these are what the weights are. They look sort of like entropy weights. But the equation for the value of the portfolio it generates, first you have the change in the generalized entropy. But the other part is you have the gamma mu star. This is the excess growth rate of the market divided by SC. And you see, if we can bound this away from 0 somehow, and if we know that we have upper and lower bounds on SC, we're going to be able to prove some sort of arbitrage here, of relative arbitrage versus the market. And so we have a theorem already on long-term relative arbitrage. Suppose the market's defined for all t, positive t, and there exists an epsilon such that, positive epsilon such that gamma mu star is greater than epsilon. In other words, gamma mu star is bounded away from 0. For large enough t, there exists strong relative arbitrage versus the market. And this is an easy proof because you just consider that generating function. And you integrate it, and this will be the difference between the end point and the starting point of the relative values, okay? And you have the log of these two terms, and then you have this integral over here. So the worst that these terms can do is the numerator can be c and the denominator can be c plus log n. You can't do any worse than that. And then what happens is, because you can bound this away from 0, and we have that one bounded away from 0 by epsilon, if you have t large enough, you're going to get arbitrage. So you can immediately see that over the long term, you're going to have relative arbitrage in this case. If you can have relative arbitrage, it means you do not have an equivalent martingale measure. You cannot have an equivalent martingale measure. By the way, if you really wanted to see the details on this, you can also see that the ratio here is going to be bounded. So these doubling problems that come up in some are taken care of by these generating functions. You don't have to worry about that. So you get long-term relative arbitrage if gamma mu star is bounded away from 0. Now, it might be nice if that would produce short-term relative arbitrage. All right? But it doesn't. Is the problem. It doesn't quite do that. Instead, you have this more complicated proposition. And this says, okay, for t bigger than 0, so now we're stating what t is. We're not just saying for all real numbers. So we say for t, suppose that there exists an epsilon bigger than 0, such that this is going to be bounded away from 0 for all t in this arbitrary interval. T was arbitrary. Okay, now we need this extra condition. Suppose also that for the entropy function, the essential infimum over the first half is less than or equal to the essential infimum over the second half. In other words, the minimum of this thing has to go up, is the problem. Then there exists relative arbitrage versus the market on 0t. Now, when I first saw this, I thought that this was completely worthless because you can't have conditions having to do with essential infima in the hypothesis of a decent proposition. But this is the best that you can do, okay? And this an example that Johannes Ruf dreamed up, and it's been elaborated now quite a bit, showed me that this is actually the case. And we'll get into that in a while. Yeah, we have plenty of time. Okay, so we're going to prove this. We're going to see how this is done. Now, this is just, I'm not saying strong relative arbitrage. This is just relative arbitrage. So here's what the proof looks like. And this is really an example because the entropy function is a rather specialized function. There could be many versions of this theorem with other generating functions and things. All right, so you let A be equal to the essential inf in the first half of the interval. And we know that this is bounded away from 0 there, okay? So if that's bounded away from 0, we can't have everything be constantly equal to 1 over n, which would be a problem for it. So we know then that the A has to be less than log n, because only if everything's 1 over n is the entropy function equal to log n. All right, so that means we can find a delta such that A plus 2 delta, this is the essential inf, is less than log n. Okay, this gives us enough room to operate in. And also, by the definition of the essential inf, that the probability that you're going to drop below this value by time t over 2 has to be positive, okay, because that's the very definition of essential inf. All right, now what we do is we define a couple of stopping times, all right? What we do is the first one is we define tau 1 to be the first time that this is less than or equal to A plus delta, all right? Now, the probability that this is less than t over 2 is going to be positive for what we just said beforehand. It could be equal to 0, you know, because we could start underneath that point. All right, but at least it has a positive probability of being less than t over 2. We now define a second stopping time, which is not entirely necessary, but I like it for aesthetic reasons. I'll tell you why later. The second stopping time is after t1, after tau 1. If we go back up and the entropy function goes past A plus 2 delta, then we hit the second stopping time. Now, what we're going to do, we define now this generalized entropy function, S delta. We use the same delta that we had before. All right, so we know that that's bigger than or equal to delta because of what we've said previously. And we have this equation. This is simply the equation for the generating function. And so there are two pieces. We want to figure out how the value changes between tau 1 and tau 2, how the relative values change in that period of time. And so we have the change in the generating function, as always. And then over here, we have this integral. And this is bounded away from 0, and we have some control of that. All right, now what our strategy is going to look like is, here's the picture. We start out someplace under log n, okay? And if we're up here, we could just go the whole way across, in which case nothing's going to happen because it never gets down far enough. We could start down here, in which case we'd start everything tau 1 would be at 0. Okay, but in this particular case, we start up here, and we're going to wait for a little while. Then we're going to hit tau 1 down here, all right? And at that point, we're going to start this portfolio, and then we're going to continue. Now, if we go up a little bit, we're going to get out because we're ahead at that point, and we're going to be winners as well. I won't go back into the political ramifications of that at the moment. But in any case, we get out when you're ahead. But we might not actually get up here. So the question is, can we survive if this thing just wiggles down and goes off down at the corner? And this is what we have to show. So let's go and now look at how this works. Okay, now first, we assume that tau 1 is less than t over 2. Okay, otherwise it's boring. If it's not less than that, we just go across and we don't do anything. Okay, now this is if tau 2 is less than t. That means we've moved up and we've gone through that higher barrier. Then this is what this is equal to, essentially. I mean, this could be less than that because of the fact that you could have started under that. But we have this first inequality because here we know that we get out with this valued at a plus 3 delta. This has to be positive because all of these terms are positive. And so we're ahead and we win and we quit. Okay? Now the hard one comes up. Suppose that it never goes up through the 2 delta line. In other words, now we have to prove that we can somehow deal with that. So what's going to happen now is that tau 2 is going to be equal to t. And we know that this is bounded from above. Now, it's been pointed out that we knew it that anyway because it can't be any greater than log n plus delta or something like that. But we'll forget about that for the time being because I like this method. We have a bounds, upper and lower bounds on this. So we're now going to look at this difference. What actually happens here? We know that because of what's going on there, that this term has to be at least a plus delta, because this can't go down below the a line, right? Okay? And this one can be at most a plus 2 delta because that's where the tau 1 would have started. And then we get this other term, which is epsilon t over this, because we know that this denominator here is less than or equal to a plus 3 delta. Now we have to look at two cases here. The first case is that a equals 0. If a equals 0, this is what the equation comes out to look like. And you just solve this and make that equal to 0. This turns out if you plug that into here, you're going to get a equals 0. And there's a strict inequality there, so the thing works. All right? Now, if a is bigger than 0, okay, in this case, if you take this limit as delta decreases to 0, it turns out it's going to be equal to this. That's pretty clear. So for some small delta, it's already going to have to be positive. So we know that this is going to be positive, and therefore this will be positive, which is what we needed there. Now we form the portfolio over the whole period of time. So we're going to form a portfolio nu, which we start out with mu, okay? If it never hits that line that we're talking about, the a plus delta line, we just keep with mu the whole time. But if we hit it, you see, then we immediately will switch to pi, the portfolio that we've just constructed, all right? And we'll stay with that until we get to tau 2. When we get to tau 2, we'll bail out and go back into the market. We retract all our bets at that point. All right, now what happens under those circumstances? Well, it's pretty clear, but we have it written down here anyway. Okay, if this is tau 1 is equal to t, this is for the whole thing, and it's simple. Okay, if tau 1 is not equal to t, in other words, something has happened in this case, then because these log returns are cumulative, you can just add one to the other, we find that the portfolio performance here for the eta portfolio is exactly the same as this, because when it's mu, there's nothing added or subtracted. And so therefore, this eta portfolio has outperformed there's at least a positive probability of outperformance. So in this particular case, where you have that strange condition on the essential infima, you get short-term arbitrage, short-term weak arbitrage, but that's enough to show that you don't have any equivalent martingale measure. And so now we have one possible interpretation of adequate volatility, all right? Suppose that gamma star mu is bounded away from 0 in this interval, okay? And suppose that the market is strongly non-degenerate over that interval. Then there exists relative arbitrage in the market over that interval. There are two possibilities. If it's diverse, We know that diversity and strong non-degeneracy through a few steps previously would give you arbitrage. If it's not diverse, that simply means that A has to be equal to 0. Non-diversity means that the essential inf is 0. And then we get short-term relative arbitrage on the other using the proposition that we just had. There's a note here, you can apply it to a submarket. That's not very interesting. The thing that is sort of interesting here is if you were a portfolio manager, how would you actually implement this? It's sort of problematical because you don't know which case you're in, you see. So from a portfolio management point of view, this isn't terribly useful. It does tell you whether it would be safe to assume the existence of an equivalent martingale measure or not, and which means that it would not be safe to do that. All right. The question is now, with that essential inf, why do we actually need the essential inf? Can't we get rid of this? And this is an example that was inspired by Johannes Ruf, and then Yannis Karatzis worked on it for a while. And then we all collaborated, and this, I think, is the simplest form it's in at the moment. And it's a little bit involved here, but you look at this, and this is actually a market with just 3 stocks in it, okay, which is good. And you don't actually have a stochastic differential equation, which simplifies life a certain amount. So we've actually explicitly written the x's out, and it's written in this term. So let's look at, this is a 3-dimensional Brownian motion, so those are independent. We have this complicated inequality here, which you should just assume is okay under the circumstances, because it's very tedious to go through all the details. Now, phi here we're claiming is a martingale driven by B, which has these 2 bounds, A and 3A, or the lower and upper bounds for some number A, which falls between these numbers. Okay, these xi are martingales. Well, why are they martingales? Well, this is a well-known martingale, okay? We just claimed that this is a martingale. A third, by the way, is a martingale, too. And it turns out that this whole thing with the e to the t over 2 and the cosine is a martingale. If you go through and do the stochastic differential equation, you'll see that that works. Okay, so the xi's are martingales. Products of independent martingales are martingales. So that's a martingale. Okay, since they're martingales, relative arbitrage obviously doesn't exist. And these motions, there are 3 different motions here. I'm going to draw a picture in a minute. This is radial motion from the center of the R3, okay? This induces radial motion centered at 1/3, 1/3, 1/3 in the middle of the simplex. And this theta, which is a Brownian motion, induces rotational motion. So I'm going to try to draw a picture of this. And so we have to, we'll test my artistic talent. So those are the 3 coordinates. We'll put the 1s in here. Let me go over to that. So this is the simplex. You're going to get a third, a third, a third is somewhere like this. And then you're going to get these circles. Whoa, that missed, but in any case. And so you have this annulus, which the annulus lies on the simplex. Okay, this is a 1, and a 1 up there. And this annulus is expanding at e over t, e to the t over 2, I should say, e to the t over 2. So you have this expanding annulus, and your process lives within this zone. All right, so you can see the problem with that is the thing expands out. The essential inf of the entropy function is going to be going down. So this is the way it's not supposed to go. It's going to go up. So that lemma, or that proposition that I proved earlier, you really need the essential inf in there. You can't just scrap that, as I wanted to do. All right, now I'd like to convince you that such a process actually exists. And here's the way you structure that. Okay, you first define an F martingale. F is the filtration of those three Brownian motions. You define it by taking a parabola, okay, and then having the Brownian motion with this as the variance function for the Brownian motion. All right, now the parabola is sort of shaped like this. So if you look at the edges, there's a slope there. And we've seen other situations like that. And if you have a slope, the thing can't explode through the slope. It's stuck. It's just like the stock price processes can't explode into negative territory. So that's how I would reason it. Yanis Karatzis, who's much more precise than I am, of course, invokes, the Feller's condition on explosions and so forth. And it turns out, whatever you do, you find that this C process is stuck between plus and minus A with probability 1. All right? And then you just slide the thing over by 2 alpha, and that gives you the phi. Note that this is the quadratic variation that we have here. Quadratic variation is it's never 0, but it's not bounded from below. Okay, so we're not going to be able to, we have no hope of getting strong non-degeneracy here. So now we'll go back and look at this again. Now we have the things written out more clearly. So we have this martingale, we have this martingale, and we have that martingale over there. And I've colored these things first so that you can see which is which. But also, this is sort of like a Lego game where you can take these pieces out and change them and move them around in this particular thing. Okay? In this particular case, there is no relative arbitrage. These are, after all, martingales. You're not going to have relative arbitrage under those circumstances. Okay? Now, we can knock that the phi out. Okay? The phi is what gave width to this annulus. Now we have something that lives on an expanding circle on the simplex. Okay, so now we no longer have a non-singular covariance matrix, because in the other one, if you look at the directions here, see the phi direction would be movement radially from the 1/3. The theta direction is circular direction, and the w there, the e to the wt minus t over 2, is radial from that. So that spans R3, but we no longer can span R3 because we just eliminated the one that was radial from the 1/3, 1/3, 1/3. So now we have a lower dimensional movement, but there's still going to be martingales, okay? Everything that was there before is still there. All right, now, the next step is we get rid of the e to the t over 2. Okay, now we have a situation where it's not a martingale anymore. Okay, you take that out and the thing is no longer a martingale. So what happens now? Well, certainly it's not strongly non-degenerate, but that's about all we can say about this. Look at what happens, okay? We go to the next one. You look at this model, the weights for these lie in a circle in the simplex centered at 1/3, 1/3, 1/3. So this generating function, which is just the distance from the origin, is going to be constant. So you write the equation for the generating function, and you see that, it's going to generate some sort of a portfolio. It doesn't matter what it is for the time being. And this first term here is just going to go away. I mean, the thing's constant. The derivatives of the thing is going to be 0. So you're just going to get a gamma minus gamma star, which we know that this is bounded away from 0, okay? By the way, these computations with trigonometric functions are very tedious, and I'm saving you the pain of having to watch them. So I've dropped them all out. If you want to check them, this will probably be included eventually in a paper. All right, but you get instantaneous relative arbitrage in this case. What happens is the instant that you start your portfolio, because this is negative, it's going to go behind the market. It goes instantly behind the market. And then you use the argument where you take the short side of that and it'll beat the market. Okay, so you get this instantaneously. Now, this is not just relative arbitrage anymore. This is going to be regular arbitrage too. Suppose you had a standard numeraire, which you might as well assume is just a constant process 1. Because of the fact that you can never get behind here, there's no problem with using that numeraire. So this is both relative arbitrage and standard arbitrage at this point. Okay, so now what's the next Lego move that we do? Well, we now have knocked this. We left that out so they're not martingales. Okay, and now we have arbitrage. We have the phi in here, so this is now moving between those two things. But in this particular case, it turns out that the essential infimum is fixed. So we can invoke that proposition. Now, you can either say it's obvious, which is what I would be tempted to do, or you can invoke a theorem of Brueggemann and Roof that shows that in one-dimensional diffusions you can move out arbitrarily quickly to any point. So now we'll move one more Lego piece. Oh, what we're actually doing is, what's this doing here? That's a good question. This is essentially a placebo. Okay, well, it does give you motion, radial motion. It does make it it does mean that the covariance matrix is non-singular. But it was put there for the placebo effect. I mean, everyone knows that this is a martingale, and so you feel this is something they're used to. So then you're more likely to believe that this other piece over there is a martingale. But it's not really doing anything constructive, so you can get rid of it. Boom, you take it out. Well, okay, since you've taken it out, you're no longer going to have it's no longer going to span the space. So you're not going to be able to say that the covariance matrix is non-singular. But now what you have is you have these processes living on the simplex. They no longer move up and down from the simplex. All right? And we can go further than that. We can put some other process in here. All right? Now, by the way, these are those who are martingales, of course. If you made them non-martingales, then you'd have the thing. But okay, this is the Lego move we did now. We put in some other process, this kappa T process. Now, whether this is a martingale or not a martingale is not going to matter. We're not going to have arbitrage in this market. We're not going to have relative arbitrage in this market because the relative arbitrage depends just on the weights. All right. And when you do relative arbitrage, you're going to factor out. This actually is the value of the market here because these things add up to 1/3, 1/3, 1/3, which is 1. They're on the simplex. So depending, you could have a non-martingale here, and you wouldn't have relative arbitrage, but you might perfectly well have standard arbitrage. And in the other examples, by moving other pieces of this, you can get relative arbitrage without standard arbitrage and vice versa and so on. And you might actually be able to figure out how to generalize this to higher dimensions if you feel like it. But we don't really know what the ramifications are. These are a few of the possibilities. You move the Lego pieces and you get different answers. In any case, the conclusion that we are currently at is that if gamma mu star is bounded away from 0, this will generate relative arbitrage, but not over arbitrarily short intervals. If you want it to operate over arbitrarily short intervals, then you need something having to do with the essential infimum. Now, some of the papers that are involved, this is the one I mentioned about Brueggemann and Roof about one-dimensional diffusion moving quickly. Okay, this is stochastic. This is my book from 14 years ago, where these portfolio generating functions are explained. This is the example that was in proposition form with using for the relative arbitrage. These are the variations on the example of Karatsas and Roof. I told you that's where the genesis of this was. And this is the old paper by with Yanis and Kostas, where we show that there's short-term relative arbitrage if you have diversity plus strong non-degeneracy. And this is hopefully the paper that eventually will be published by Fernholz, Karatsas, and Roof once all three authors get their acts together. And that, I think, is it. Thank you very much.